find with him, he just tends to repeat the same thing 5 times. We're looking at a video, and we're looking at a graph. Okay, now we look at this graph. We see this graph is discrete, and we're going to make a discrete graph. We do it. So, but he has a good concept behind that. So let's see how we use this central limit theorem. Assume the training heart rates of all 20-year-old athletes. All 20-year-old athletes are normally distributed. I have a normal curve with a mean of 135. This is my population we're talking about. And a population standard deviation of 18 beats per minute. We found this old information. We knew this old information, as shown in the figure. It's in your book somewhere. Random samples of size 4 are drawn from this population, which also happens to be extremely small, and the mean of each sample is determined. Find the mean and the standard deviation of the sampling distribution of the means. Then sketch a graph of your sampling distribution. All they want is this. The mean of your sample will be equal to the mean of your population. So what will the mean of your sample be? 135. Good. I pull off all my information, and I need to remember to do this. This is something we didn't have to do before. So when you see something that takes a sample size, always underneath your information write n equals. I've got to do something with that. So that tells me you have a sample. So I want to see, now the only thing that's going to change, my mean is going to stay the same, but my standard deviation is going to say standard deviation divided by the square root of n. That's where that n comes in. So we take his standard deviation and we divide it by the square root of 4. And the square root of 4 is 2. So 18 divided by 2 is 9. That's the only thing that's going to change. So now when we go to use your z-score formulas, we're going to use the standard deviation as 9. What it did is this. It told us that your population was normally distributed. Here's my 135. Here's my plus 18, plus 18, plus 18. My mean is going to stay the exact same for this guy. The exact same. But look, my standard deviation is going to be like half of this now. So my curve is going to go like this, around the mean. I cut my standard deviation in half. I have less variance from the mean. That's why they call that a sampling error of the mean, because I want to make sure that I'm close enough in here so that I'm not off on my samples. I've got to allow for a little issue with my samples somewhere along the line. So this is the only thing that's going to be different, is your sample standard deviation. Okay. So make sure you have that. All right. So why do we use this? Let's see why we're going to use this now. For you guys that were out yesterday, we spent an entire period going through this theorem to develop these two things. That the mean would stay the same, but the standard deviation would shrink. And we did find at the end of the period, n has a big play in this. If I change n now to say 36, if I increase n, I'm 18 divided by the square root of 36, so I'm 18 divided by 6. That's now 3. So the larger the sample size, the smaller the standard deviation. The smaller the sample standard deviation. Makes sense? Because I'm dividing by the square root of a larger number. So that makes sense. Okay, so let's do it. Let's get to the nitty-gritty here. Yesterday we talked a little bit about your z-score formula that you know and love. And this was for a population. So we have to change this slightly for your sample. So we're going to change this a little bit around for your sample. So your means are going to stay the same. But now your x value is not going to represent a real x, one person. It's going to represent the mean of all the sample means. So this x bar stands for the sample means. And you're not going to notice the difference, really. It's going to say the sample means of all the heartbeats found in your sample was blah, blah, blah. Or we're going to set it equal to whatever they gave us for the population. The one thing that's going to change is this stuff. So all we're going to do is do this, and this is the major change right there. And you're going to know to do this whenever they give you an n, a sample size. The hardest part is figuring out when do I divide by the square root of n. Well, you only do that when you have an n. If you don't have an n, you have a population. And then we're back to your regular z-score. Okay? So we're ready? Okay. You randomly select 50 drivers, age 15 to 19. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Assume that the population standard deviation is 1.5 minutes. This is prior information. Okay? They've done this before. So they took the standard deviation before and they said, I'm letting you use the population standard deviation. Because once before we figured this out. So we're going to say, okay. It's in your book as well. You're going to need to look at those cars to see what the minutes is. So I'm looking for the age group. It's on page 266. If I'm looking for the age group 15 to 19, what does their population mean? 25 minutes. So I needed to know this. I had to take that off the chart. Everybody see where we got this? Ages 15 to 19, their mean time is 25 minutes. I want to know what's the probability that they spend driving time between 24.7 and 25.5 minutes. Okay, what's my n? How much are in my sample? You select 50 drivers. This is your n. This is your sample. Normally, does it ever tell us we select anything? We always look at the population. We always pull one random person from the population. But now we're doing a bunch of these little samples, and we're going to take their sample means. So the only thing that's going to change now, my population standard deviation was 1.5. This is going to change. My standard deviation for my sample means is going to be 1.5 divided by the square root of 50. This is the only change right now. I see this different, and as a result, I have to do this. This is how you recognize a sample. Otherwise, it's going to look like a population one. And we don't want to do a population one because that would be wrong. Okay. So when we put this in here, we get 1, 2, 1, 2. I just made it go to 3 decimals, but you don't have to make it go to 3 decimals. When we put it in the formula, I'm going to leave it as 1.5 divided by the square root of 50. And then you're just going to put that whole thing in your calculator. Now, here's my graph of the situation. I know we can do this. I know this makes a normal distribution. Why? It never told me that. N is greater than or equal to 30. Good. n is greater than or equal to 30, so I know I have a normal curve. Otherwise, I can't do this. If n was less than 30, and they didn't say this approximates a normal distribution, done. We can't do it. My mean goes in the middle. Okay. Now, normally we would go out 1.5, 1.5, 1.5, 1.5, and do it that way. But we have to go out this way. So let's cut this standard deviation, since it's 1 decimal point there, down to 1 decimal point. This standard deviation was 1 decimal point. We'll round the standard deviation to 1 decimal point. And again, we exaggerate your curves. Because remember before when I took that curve and then I squished it together how thin it would be? You'd never be able to make your bars in there. So this is an exaggerated sample curve. It would come from this big curve, and then I'd have to squish it in and go like this. So this is the curve I'm looking at right now. So I'm going to go like this. The rest of this is going to be exactly the same. And I'm going to go up 0.2, 25.2, 25.4, 25.6. Look at how close together that is. I mean, 1.5 is small as it is, but 0.2 is very small. 24.8, 24.6, 24.4. So I want to know, what is the probability? I come down and I write my probability statement that x is between 24.7 and 25.5. So I find 24.7. There's 24.8. In the middle is 24.7. 25.5. There's 25.6. There's 25.5. That's a big chunk of my curve. Would you estimate to be 50%, a little more than 50%, a lot more than, somewhere around there? Would I say over 50 or under 50? Over? Good chunk of that curve, right? Over 50%. Now, how did we do this before? We found the z-scores for your x values. We found the areas. We subtracted the areas. So we're going to do when x is 24.7 and when x is 25.5. But remember, my z-score says take this, subtract it from the mean, divided by this guy. If you want to put 0.2 in there instead, the rounding's a little bit different, but you can do that. I would prefer this part, let the calculator do the whole thing. And we're going to do the same thing here. We're going to say the x minus the mean, that doesn't change, but this is the part that changed. So you're going to put those in your calculator, and you're going to find your z-scores. Really, this is the biggest change right here. The only really visible change. And the fact that we had to set the curve a little differently. Okay. So try putting this in your calculator and see what you come up with. Remember, I'm talking about not just one sample. Even though they don't say there's multiple samples, they sample and sample and sample and take the sample mean of all those sample means. So what did we come up with for a z-score here? Negative, what? 1. Did you get negative 1.41? Okay. And this one? 2.36. If you struggle with this, guys, use your fraction bar. Use your fraction bar. This is really important how you put this in. use a fraction bar. Alpha y equals. On the top, I say 24.7 minus 25. On the bottom, use another fraction bar. I say 1.5 divided by the square root of 50. Make sure you watch those parentheses. If you're using the black calculators, the 83s, and they don't have a fraction bar, you have to put parentheses around the top, and you have to put parentheses around the bottom. This is what's going to give you this answer. Agreed? Okay. Now, the next thing we did was we looked up these areas on your z-score table. And we subtract the higher, which is 0.9909, minus the lower, which is 0.0793. So we do 0.9909 minus 0.0793, and we get 0.9116. It's a big chunk of my curve, right? It's a good size of my curve. And we said, yeah, well over 50. So we were good. We were very good. Now, what does this mean? If you go back to the problem, it says, what is the probability that the mean time, they want the mean time of all their sample means, will fall between 24.7 and 25.5, have a very high probability, have about a 91% chance that the probability for these sample means will fall between 24.7 and 25.5. By squishing it all in, this helps my sampling error. That's why we divide this out. We make it a little tighter in the field there. Otherwise, we'd be far more spread out on this. Far more spread out. So I have a good probability that my sample mean of all those samples are going to be between 24.7 and 25.5. We didn't change life too much, except for this. This was an in-between, so this involved a little bit more work. For those of you that like the calculator, this works real well in your calculator. Normal CDF. Your lower limit, give your x values, 24.7. Your upper limit, give your other x value, 25.5. And for the in-betweens are really nice on this. The mean, 25. Standard deviation, you got to give the sample one. 1.5 divided by, put this in, let the calculator worry about it, divided by the square root of 50. Come back down here and paste. See your answer? The only difference in here is the rounding. We rounded both of our z-scores. The calculator has its own rounding algorithm. So if you like the normal CDF, you bypass all of this. On the in-betweens, they work really, really nicely. And you put the standard deviation right in as your sample standard deviation. Let the calculator do it. Okay? Does this make sense? Almost like we did before, isn't it? And when we do area to the right, everything is going to be the same as we did before. We're just going to have to do this one little extra step here. That's it. Basically, that's the only difference that we do. It's taking your standard deviation, dividing it by the square root of radical, the square root of n. Okay? I'm going to have you guys work. The only change you should see in this one is the fact now that you have 100 drivers instead. Before we had 50, now we have 100. We're using the same information. We're asking for the same probability statement. Remember, we put x in the middle because this is an x value that they give us. Make sure you can write a probability statement. And the only thing that's going to change is your standard deviation. Your mean is going to stay the same, but your standard deviation is now 1.5 over the square root of 100, which is 10. So it moves it one decimal place over. So your new standard deviation is 0.15. What was it before? 0.2, right? So we got a little bit smaller. The larger the sample size, the smaller the sample standard deviation. Because I want to make sure I got a good representation of my sample. So I start at 25, and I add 0.15, 25.15, 25.3, 25.45, and then subtract 24.85, 24.70, and 24.55. So I want between 24.7, which is right here, right at that line, and 25.5, which is after this. Look at the amount of my curve that I want. Now, did you have to do a Z1 for this guy? Did you have to do the Z formula for this one? If it falls right on the line? Stephen, what was its Z-score? -2. So this guy had a Z-score of -2. It came right on my graph. I don't have to be bothered doing that. My next one, yeah, should do that one. 25.5 minus 25 over the standard deviation divided by the square root of 100. Since that was a terminating number, you can just substitute it with 0.15. And you got 3.333. Find your areas and subtract your areas. Okay. Use your formula, use your calculator to help you find the areas, use your table to find the areas. Anybody have the areas for these guys? Well, I do. I think I do. So I'd like to show you. Some of you guys like tables. I want to keep it with the tables. And then if you like to do your own, you can do that. This is 0.9996. This was 0.0228. And always subtract so that you get a positive area, because areas can never be negative. So when I subtract these, I get 0.9768. So because my standard deviation got smaller, pushed me closer to the mean, my curve is much narrower even, I'm going to cover more space. So I have about a 98% chance that the sample mean of all these samples will fall between 24.7 and 25.5 minutes. Okay? It tweaks it a little bit using the standard deviation divided by the square root of n.